poetry mode. I mentioned in a previous lecture that I'm a really big fan of the minimum number of marks on the page that make it easy and clear to write the code and for other people to read the code. And one of the ways that Ruby supports this is through poetry mode. Here's an example of a legal Ruby statement that came from one of my apps using poetry mode. And you can almost read it aloud and figure out what the code does. Redirect to login page and return unless logged in. Code does not get much more transparent than that. But the reason this is legal is because when parentheses around function call arguments are optional, in other words, when the parser would not be confused by omitting them, Ruby lets you omit them. And also because braces around hashes can often be omitted if the context is unambiguous. So for example, if we rewrote this with fully parenthesized syntax, we could see that redirect to login page, this redirect to is a method that expects one argument, and is a standard Boolean connector, which you've seen before. Return, well, in this case, return isn't returning any explicit value, so it's like a function call, but there's no argument. And logged in happens to be another function. I didn't add the empty parens around it, right? So again, as you get used to the language, it'll become very natural and very clear to you when it's okay to leave stuff out. Here's another example. Dave alluded in one of the earlier lectures about the ability to write things like a should be greater than or equal to 7 when you're expressing test cases. So how can that possibly work? Well, again, if we parenthesize defensively, should is really just a function that takes one argument, and the argument that it takes is the expression b greater than or equal to 7. In this case, I happen to know that b isn't a variable. It's actually another function call. It's a method call. So in the poetry mode example, I've been able to omit both the empty parens around b, which tell us it's a function call with no arguments, and the parens around should, which capture its argument. One last example, and this is an example of omitting braces when it's obvious from context that something is a hash. This is an example of a call that is very common in Rails applications, saying to create a URL that links to a particular procedure in your program that handles some user interaction with the web app. So what we've done here is there's actually two things we've omitted. This is a function of one argument, and the argument is a hash. So because it's unambiguous in parsing, not only can we leave out the parens around the function argument, we can leave out the braces that normally would go around the hash literal. Now again, the first time you see this, it's a little confusing. You might not always realize when it's acceptable to do it and when it's not. So when in doubt, you can always parenthesize defensively. But in general, you'll very quickly get used to when this makes sense to do, and you're going to find that it makes your code much more readable. Our next topic is one of the areas that is, at the same time, one of the most powerful things about Ruby, and also one of the things that people new to the language get a little tripped up on, because they're features that are not nearly as common in other modern languages that most people are using. Certainly not so in Java, a little bit in Python, but even there, not so much. So let's talk about blocks and iterators and some of the functional idioms that they enable. Functional programming, if you had the good fortune to take a course that no longer really exists here. It's called Structure and Interpretation of Computer Programs, and it used to be taught in a language called Scheme. And that course, among other things, had an introduction to a really deep idea called functional programming that has been in the languages community for a long time, and some people, including me, think it doesn't always get the airplay that it should. And what we're going to talk about in the next few minutes here is how can techniques from functional programming actually help us rethink some pretty basic programming concepts, like, for example, iteration, something we do so often we take it for granted. We do for loops, we traverse data structures, and more importantly, why should we care? Why is it worth rethinking our approaches to some of these pretty fundamental programming constructs? So let's just start out with some examples. And as usual, you'll get used to seeing the examples, and you'll quickly come to realize, as you use the language more, why these are valuable things that you can do. Here's a collection of 3 things. An apple, a banana, and a cherry. It's just an array of 3 strings. And I can say, with each string, just print it. So that looks like a loop, right? The tendency, if you come from an imperative language like Java, is to say, oh, I get it. That's like a way of writing a for loop over the array elements. It's not. Take it on its own merits. It's each. Here's a collection, and with each element of the collection, do something. Let's do a couple of more examples to drive that home. You could do this, but that's really just syntactic sugar for something that's more like this. Right? What's going on here? What is this up to business? Well, we know it's a method call. We know it's a method call on an integer. We know it's a method call that takes one argument, and it can be followed by a block. A block is just a lambda expression. It's a procedure that has no name. In this case, it's a procedure of one argument, num, and what it does is just print out that num. But really, that's what it is. It's a procedure. It's a function call, and what I'm really saying is, I'm going to generate a list of numbers, and for each one of them, I'm going to call a function passing that one thing as an argument. Here's another shortcut that Ruby provides. Rah, rah, rah. I've also, in this case, substituted braces for do and end. Less common of an idiom, but sometimes you'll see it. So don't be too confused. Whoops. There we go. Sorry about that. Don't be confused if you see the idiom of substituting braces as opposed to substituting braces for do end. So what's going on in all these other examples? I mentioned this briefly in a previous lecture, but what all these examples have in common is that we're allowing the objects manage their own traversal. So in this case, we have a range of objects, the integers 1 through 10, and we're saying traverse yourself, and for each element that you give me back in the traversal, I'm going to provide a function that you call with that element as an argument, an anonymous function, an anonymous lambda expression. Your friends will be really impressed if you use that word regularly in conversation. They'll also stop inviting you to parties, but whatever. So that's an example of range traversal. Well, what about this thing with arrays? Well, we saw that we could take an array and say, for each element in the array, again, I'm going to give you a function, and you're going to call that function with each of the array elements. So what's interesting between these is that you have no idea as a programmer internally what mechanism is being used to grab each element and provide it to you. You're giving that responsibility over to the target. You can do a similar thing with hashes. Remember that hashes have keys and values, so there's actually a couple of different constructs provided for going through the key value pairs. You can say for each key, give me that key and do something, or you could say for each key value pair, because the anonymous function can take more than one argument. It could take 0 arguments, in fact. Again, the simple example I gave before, 10.times, well, that's really just a shorthand for something like this, right? Except that it's an iterator of arity 0. It takes no arguments, because if you're saying 10 times, presumably you don't care about the value of the index. If you cared about the value of the index, you would do something like one of these first cases. So what this leads to is something that a lot of Ruby programmers call expression orientation. You don't think in terms of, I'm going to do something to this collection. Instead, you think in terms of, hey, collection, I'm going to ask you for things, and I'm going to do things to your elements. So for example, I can have a collection X, which is just an array of strings, and I can say, sort yourself. I can say, take your unique elements, which, by the way, what does that do? It returns a new copy. So X is not being modified here. No X's have been harmed in the preparation of any of these examples. I'm getting a new copy, which is X with the replicated elements removed. And then I'm going to reverse that. So I get banana, cherry, apple. There are versions of some of these that are dangerous. Remember I said that sometimes if you see a function name that ends with bang, it means this function is dangerous, or it may have side effects, so use with care. So in some cases, like reverse, there is a variant that ends in bang that does modify the receiver. So X reverse bang, or X reverse, actually means X will be modified. There's also map. If you've used language like Python or even Scheme, map is for each element of the array, I'm going to do something to each element, and the result is to return a new thing. So whereas the result, before when we were traversing the elements, we were just saying, here's a function call, and it's going to do something with each element, map goes further and says, actually, the result of the overall map is a new collection in which each element has been in which each element is the result of calling that the anonymous lambda. So in this example, I take my original collection of fruits, and for each element in the collection, I'm going to call reverse, which reverses a string, returns a new copy of the string with the elements reversed. So the result of this intermediate step is just an array in which each of the words has been individually reversed. Oh, and by the way, since the result of the overall map is itself a new collection, I can call sort on that. So what you'll see in Ruby is you'll see A.B.C.D. You sort of build up a list of things you want to do. It's almost like a Unix pipeline. But the idea that everything returns a copy of something, it has a value, it evaluates as an expression, and then you can continue to do more things on that expression, that way of thinking really comes from functional programming. And we're going to see some cases where it's very, very useful. Here's another one that Ruby provides, collect, which says, give me every element of your collection, and I'm going to collect all the elements for which this function returns a true value, right? And one thing that you can test for is whether a string includes a character. You can test whether an array includes a character. In a moment, we'll talk about why things like include seem to work all over the place with many different classes. Duck typing. This is fun. So, I keep saying, right, Ruby emphasizes what do you do, what methods do you respond to, instead of emphasizing what class are you. So the question is, why should you care about this, right? How does this encourage productivity? What kinds of reuse does it buy you? So an informal and humorous name some people have used to refer to Ruby's implementation of this is duck typing. And you may have heard the colloquial expression that if it looks like a duck, it walks like a duck, quacks like a duck, well, might as well treat it like a duck. So what we're saying is if you have an object that responds to certain kinds of methods, you just should treat it as the thing that it looks like it is. If it responds to things like give me each of yourself or reverse yourself, well, what is it meaningful to talk about those operations on? Well, it must be some kind of a collection. So you say something quacks like a collection in Ruby, it means, you can expect that thing to respond to most of the same collection-oriented methods that a normal collection, like a built-in collection arrays, would respond to. So if you've used interfaces in Java, you'll notice that this is kind of similar, but I think this is actually much easier to use. Whoops. Sorry. So as an example, if I call sort on my list, what does that actually mean? Well, suppose my list is something like this array of integers. You can imagine what it would mean for sort to operate on that. What if it was a list of strings? You can imagine for what it means for sort to operate on that. Or even a list of symbols. Or even what you get back from I/O read lines, which is all of the lines in a file one line at a time, right? This last one is basically a way of saying sort this file. So why does this work? To get the answer to the question, we'll introduce one new Ruby construct that doesn't really appear in other languages. And in languages where it does appear, the term module doesn't mean the same thing. In Ruby, a module is a collection of methods that aren't a class. So you can't instantiate it. There are no instances of a module. It's really just a group of methods that collect a bunch of related behaviors and they go together. Now in some simple cases, the use of a module is just to collect methods like methods related to a common set of operations, like mathematical operations or constants that are mathematical operations. That's pretty trivial. The much more interesting use of modules, which we focus on, is when you use a module to mix methods into a class. So what does that mean? Suppose that in my declaration for class A, I say include the name of some module. That means that when I try to call a method on an instance of A, if I call, for example, a.foo, first it will search whether class A has that method. Then it'll search whether any modules included into the class have that method. And then it'll do the other stuff we've already talked about. It'll call method missing. It'll punt up to the ancestors. But modules essentially give you a way to say, wait a minute, add a few things to this class. I'm not done with it yet. And the reason you'd want to do that is that it's often possible, because Ruby cares more about responding than it does about classes and types, it's possible to define modules, collections of behaviors, in a way that's reusable around a lot of different classes. So in fact, it might surprise you to learn, as one example, that the sort method we used on the previous slide as an example, you'd think that it's defined on arrays, but it's actually not defined on arrays. It's defined in a module called enumerable, and the enumerable module can be mixed into any class that knows how to enumerate the elements of itself. Let me say that again, because this is a little bit non-obvious, okay? We saw these different examples of using each, and I kept saying, we're not intrusively reaching into a collection and getting stuff. We are asking the collection nicely, please give me back each element of yourself in turn. I don't care how you get them, I just want each element so that I can do stuff to it. Now what we're saying is, well, if you can do that, then there's a bunch of things that I know how to do for free. For example, if you can return each element of yourself, I can sort you. Right? Provided that your method, the things inside your collection are in fact sortable. We'll come back to that in a moment. What else could you do? If you can return every element of yourself, I can test every element against some condition. That was select and collect and those methods that we saw. So what does this mean? As a concrete example, it means that a mix-in is like a contract. The module enumerable, we're going to use as an example because it's used all over the place in Ruby. It's very common. It assumes that the target object and the class you're mixing it into know how to respond to each. right? So like I said, if you define a new class, for example, a binary tree data structure, and you define each as a way to get at the elements of that data structure, you can now mix in enumerable, and you'll get these methods for free. It will define for you predicates like all and any, collect, find, include, map, partition, a whole bunch of really neat stuff just because you agree to provide each. This is a hugely powerful behavior. Enumerable is also where sort happens to be defined in Ruby, but sort also has another requirement, which is that sort also has another requirement, which is that the class, the elements in the collection be able to respond to the spaceship operator. Remember the spaceship operator? It's kind of rolling all the equality operators into one. A spaceship B is -1 if A is less than B, +1 if B is greater than A, -1 if A is less than B, +1 if A is greater than B, and 0 if they're equal, right? And you can imagine, for whatever class you want, you can define the spaceship operator. You can define it to be sorting your colors in your favorite order if you wanted. Now, obviously, in classes like int and string, spaceship is already defined with the semantics that you would expect. But the important thing about this is, if you have a collection of things, and the collection responds to each, and if the elements in the collection respond to spaceship, then you have to do 0 work to get that thing to be sorted, right? Because what is sorting? It's taking pairwise comparisons and seeing which one is greater of the two, and in some algorithmic form, putting those things back together. And in fact, there's another module that ships with Ruby called comparable, which says if you provide the spaceship operator, which takes one argument, right? Spaceship takes one argument because there's the receiver of spaceship, and there's the thing you're comparing the receiver against. If you provide spaceship, then I will define these other ones for you. And I'll also give you happy ones like between, which tells you if one element is between two others according to sort order. So what does this all mean? It means the class of objects really doesn't matter, almost at all. Only the methods to which they respond. Let's look at a couple of concrete examples of this. Sorting a file. Well, we have file.open. That's a method that returns an I/O object representing an open file. And if I/O objects actually define each. They define it as, I'm going to return each line of the file in turn. That's a pretty sensible semantics for reading a text file. So what does that mean? I can say open a file and sort it. That's it. I don't have to provide anything because the thing that I'm calling sort on is a collection that responds to each. It knows how to yield every element of itself. And inside that collection, what is each element? Well, it's a string, right? It's a line of a file. Strings know how to compare themselves. That's part of the built-in string behavior. So with no extra work, I can reuse behaviors despite the fact that the classes are different. I can also say, which lines of this file begin with a vowel? Well, that's easy enough. We already know how to use select to pass an anonymous method to something, anonymous function. So for every line of a file, we're going to pick out the ones where this regular expression match returns true. Again, 0 additional work.